Welcome to Breadboarding. This is the fifth in the series of Breadboard video controller videos that I've been putting together using the Nanocomp 6809 microprocessor. This is the fourth step in the video controller plan. It's relatively simple what we're doing during this video. We're going to enable cursor support. We're going to modify the display enable signals so that the display fits better on monitors and on the video capture card. And we're also going to add a color register so we can software control the foreground and background colors. So let's just have a quick look at the video capture. I've tuned some of the timing signals for the CRTC. So for this display, which is 30 lines down and 80 characters across, this actually fits pretty well on both the LCD monitor and on this video capture card. But you can see that there's about half a character at the beginning and a little bit of a character at the end, about half a character at the end, which is not quite right. So what we're going to try and do here is to get it so these fit properly. And we're also going to be adding support for a cursor, which is going to be adding sort of an underbar under the currently selected character. We just need to make sure that the bar appears in the correct character position based on the CRTC register values. So if we go back to and just to show those issues in a little more detail, see, because this is just camera shot of the LCD monitor, you can see there's an area in orange here at the beginning of the line where there isn't any signal here. So that's wasted space. And then we can see here the red rectangle is around the extra characters that are appearing at the beginning of the line. If the display enable signal is correct, then we shouldn't see this. We should only see this first character. And then at the end of lines, you can see there's a smaller area of unused screen space, and you can see there's also probably about a quarter of a character appearing. So this indicates probably that the display enable and some of the timing signals are not quite right. And we're also then going to make sure that the cursor timing is right and it comes out in the right position. So let's have a look at the block diagram just to update it from where we were last time. So it's getting quite complicated, but what we've got here fundamentally is we've got our video output here with the synchronization signals and the synchronization signals and the digital analog converter signals coming out of here, and the characters are serialized by the shift register, so we get ones and zeros coming out of here to determine if we want the foreground or background color based on the bit pattern for each character. And this multiplexer currently has hard-coded foreground and background colors for foreground and background, which I think at the moment we're using white and blue for the background, and then that goes to the buffer to go to the VGA monitor. Now what we'll be doing to enable the cursor support is the CRTC produces a cursor signal, and this goes to plus 5 volts to 1, whilst the current selected character for the cursor and the particular lines which you've chosen for the cursor to be. So in the CRTC, we can choose which lines in the character we want to use for the cursor. So it could be all 16, so we had a full flashing block, or it could be just a couple of lines and we'll have an underscore type cursor. So to start with, we're going to use an underscore cursor. Now to enable that, what we have to do is add an XOR gate. So the cursor signal and the output of the shift register are just XORed together, and that will generate the effect that we want. Now the other area we need to look at is the timing signals for the shift register. So the character latch, as I've called it, that drives the shift register is probably not quite right, and we probably need to adjust that slightly so that the display looks better. So at the moment, the character latch is coming out of the clear signal for the divider, where we're dividing the dot clock down to the character clock. And what we'll be doing is adding a number of delays with some flip-flops here, and those flip-flops are going to be clocked using the dot clock. So we can effectively delay the latch signal here by 1/8 character dots, effectively. So we'll try this out and see how many of these flip-flops we need to do to get the display to look good. And then the other area is the display enable. So the display enable, we will also add some flip-flops for that, just to again tune where the display enable is triggering so that we get a better looking display. So let's just have a top-down look of the existing Nanocomp before we start to make major changes to it. So the few things I have done is there were some fly leads that we were using. So these sorts of fly leads that we were using for taking the video signals out of the multiplexer into the buffer here. All I've done is I've just wired these in with a red, green, blue, and the intensity as yellow. So I've just wired those in. as when I was putting jumper leads and fly leads going over here, it was getting a bit confusing with these wires in here as well. And what I've also done then is I've added an XOR gate down here, so we're only going to need one XOR gate here to do this. And then there's two flip-flops I've got here, which I'm going to be using for delaying some of the signals. And then this is the existing buffer as it exists already. So I've modified slightly some of the routing of the wires here just to make it easy to plug in and out these new bits. And you should also be able to see down the bottom here, I've got my the mini voltmeter down here on the last breadboard, and it just shows that's 4.94 volts. So this is right down the end here. So we've got a power rail just up here, but it just goes to show that when I was doing some of my early video card, when I actually checked, I found out the voltage down the far corner of the card down here could be about 3.6 volts if I wasn't careful. I've also added a couple of decoupling capacitors and things in, so where I hadn't got decoupling capacitors, I have added those. Okay, so in the next step, what we're going to do is to add the cursor support, and then after that, we will try and change the timing signals so that we get the display completely centered in the video capture card and also the monitor. So to enable the cursor, there are 4 registers in the CRTC that control this. There is configuration register R10 and R11 that determine the scan row that start and end for the cursor. So if we decided that scan row starting was going to be 0 and the end one was going to be 15, then that would provide a full solid block for the cursor. But in fact, in this particular case, I think we're using the values of 6D, 6F. And if we look in the source code, we can see down here that we've got the cursor parameters here, 6D, 6F. And that actually means, but start on line 13, end on line 15. And I think it means it's also going to be flashing at a certain frequency. So if we go back to the datasheet here, so I think what this means, because we've got 6 as the first nibble, then that means we're going to have blinking at 1/32 of the field rate, so it's about half a second or so. And the start, as I said, the starting lines are going to be row 13 down to row 15, so that's 13, 14, 15, so that'll be 3 pixels deep. And we can easily change it. If we change this to say to 60, for example, then you would see that we'd have a full flashing cursor for the whole inverted display. And then the other 2 registers that are also important is once we've enabled the cursor, it will default to the top left hand corner, which is 0, 0. But the cursor register here, by changing the value in here, then it should move to say the 10th character or the 80th character for the end of line, or number 81, then it will be next line down and 1 character in. So we can make sure that the cursor is moving around as we expect. So let's wire in the cursor. So what we have to do first of all is, this is the output of the shift register, which has the serialized characters coming out as 1s and 0s, and at the moment I've just joined this at the top here off to the multiplexer input that determines whether we use the foreground or background colour. The cursor signal is actually over on the bottom left hand side of this chip over here. That is running at the moment, but I don't think this is a particularly dangerous thing to do. It's not going to do any damage. So what I'm going to do is to plug in the cursor signal there. We're going to plug this into one of the inputs of this XOR gate. That's in that one there. And we're now going to change the input here to go to the other input of the exclusive OR gate. So we'll just put that in there. And now the output is going to go to the buffer, sorry, the multiplexer that we've got up here. So that's the change that we need to make. Fairly simple, a bit of a fly lead here you can see, but we will wire that in properly a little bit later on. And if we now just go to our VGA capture, you can see there's a flashing cursor in the bottom left hand corner, but you can see it's maybe a little small to see, but you can see that the cursor isn't quite in the right place. It's sort of coming out sort of halfway under the number 1 there. So when we have finished adjusting our various other timing signals, and hopefully we should be able to see what's going on there. Now if we have a look at the output of the CRTC sort of test program I've got here, you can see down the bottom here that we've got the memory addresses for the cursor start and cursor end, and the cursor address as well. So 00, DA and DB, so DB is the least significant byte, so that's going to be the one we're probably going to be changing. If we move that, then we should see that the cursor will move on screen. So the easiest way to do that is I'm just going on to the Nanocomp keypad here for 00 dB. All I'm going to do now is to put in 09 there, so I'd expect that to be around about character 10 on the display. And what I'm also going to do is to just go into the values for D6 here, 00 D6, and I'm going to change this to 60. So this should make the cursor a solid block. So all I need to do is just to execute that, and that should have updated the settings. So if we now go to the VGA capture, so you can now see on the display that we've now got a 16 line full flashing cursor, but it isn't quite in the right place. It's kind of halfway between the characters at the moment. That's what we're going to do with the flip-flops. We're going to fix that. So that just indicates that the cursor is moving, and we can obviously control the size of it. And if I go in and put 20 into that same value, so if I just go in here and go to memory 00 D6, if we put 20 in that and then we run that, it should turn the cursor off. There we go. So in fact we've successfully turned the cursor off there. So I'm just going to set that back to what we had it before. So there we go, we have the cursor back again. So we've done the cursor, however it's not quite right yet, so until we sort out the rest of these timing signals, then we need to come back to that and make sure that it's working properly later. So the next thing we're going to do is to look at the timing for the loading of the shift register. So the loading of the shift register is by this pin here at the top here, down as SL shift load, and at the moment this is coming from the signal at the top here, which is the clear signal for the counter here, and that in fact the signal for that is in fact coming out for when the QA, QB, QC are all 1, then that produces a low signal here. So that's the signal that we're currently using. What we're going to do is to temporarily unplug this signal here. So this is the current latch load signal actually coming over here, and we've actually got the dot clock down here. In fact, the output from the here at the moment that we're currently taking down on this hardwired track, and we're going to put this into the 1D. So this is the input of the first flip-flop. And now by plugging it into the various Q outputs, so I could do 1Q, 2Q, 3Q, 4Q, I can now delay the signal. So to start with, I'm going to plug it into the same one. So at the moment the timing is exactly the same as it was previously, so we're just going to have a look at the VGA capture. You can see here it's looking pretty much what we'd expect it to be. So now I'm just going to move this to 1Q. It will go blank when I unplug this, so it goes blank. Not too much different. If I go to 2Q, not really sorted it. 3Q, well, that's strange, so that's obviously just hitting some sort of threshold. And if we go to 4Q, that's brilliant. So it looks like 4Q, 4 dot clock cycles, so that's about half a character delay, is enough to make this work a lot better. And in fact, if you see where the cursor is, we set the cursor at 09. Now, this is the confusing thing about RAM. RAM starts at 0, so the 10th position is actually at 09. And in fact, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 there. So that is the 10th position, and the cursor is in fact in the right place. Now, there is still a little bit of adjustment needed. It's difficult to see it on this particular screen here, but when it's viewed on a 20-inch LCD monitor, there's a noticeable gap at the beginning and the end of the lines, and that's where we're going to change the display enable signal. So to do display enable, what I've done is just unplugged the display enable output. So the display enable output comes from the CRTC, goes through this inverter, then comes here to this on the buffer, the enable on the buffer chip. So I've unplugged that, and then what we're going to do is to use this flip-flop down here. So first of all, we need to provide a clock for the flip-flop. So that's going to be using the same dot clock that we've got down here on the shift register. The dot clock goes in there. Now we need to take the output from the display enable inverted signal over here, and we're going to treat that as our input. So this needs to go into the 4D. And then finally, we've got the display enable signal going into the buffer chip here. So if I just plug that into there, so I've got the display on the LCD monitor to my left here. I'll take some photos of the changes here. So if I just put this to 1 delay, 4Q, which is 1 clock delay, and there is still a little bit of a gap. If I now put it to 3Q here, so that's 2 clock delays, and that looks pretty good. I can't see any difference. I think that's about what the setting we need. If I just switch this over to connect to the video capture card. So here it is on the video capture card. It's probably not that easy to see the difference here. It was a very small difference, but I will upload some photos and put those into a slide so we can see what the difference is. It's very minimal, it's not a big deal, but it has made a little bit of difference to probably the end of the lines more than anything else. So this is now looking pretty good. The only other thing I was going to do was to look at the 25 by 80 display. This runs at 70 Hertz, so I'm just going to run up the program that's got the parameters for the 25 by 80 display and 70 Hertz, and then we'll have a look at those on the monitors. So this is a version of the CRT assembly program, and this has some settings which I got initially from the settings on the calculator that I showed in one of the earlier videos, and this has provided the initial starting values for here. What I have done is tweak those slightly. It took a little bit of trial and error to get these. Now these settings work quite well for the LCD monitor, and all I'm going to do is to download these onto the Nanocomp. So I will put the Nanocomp into load. We'll go into here. So this is sending the CRT 400 line 70 Hertz. So this is 25 lines by 80, and if I just execute that, that's working fine on the LCD monitor. If I just go to the VGA capture card, so you can see on the VGA capture card it hasn't quite worked properly. So in fact, although on the 30 by 80 lines I was able to get the same settings would work for the VGA capture card and for the monitor, for this one it's not working quite so well. So what I did was I've got a slightly different version of the program. So if we look at, this is one for the video capture card, and in fact I think there were 2 settings at the end that needed to be slightly different. So yeah, so we can see here that the sync position was 53 for the capture card, but 52 for the LCD, and the vertical total adjust needed to be 3 rather than that. So if we just send the SREC file for that down to the Nanocomp, and we will try that and see how that works. So we just need to find the capture card SREC. I just run that and we go back to the capture card and see if that's any better. Okay, so you can see there the capture card. There is a bit of a blank line at the bottom, which you might only be able to see when you're highlighting it in the OBS software I use to capture this, but that's much better. So what we've been able to do now is to get the timing signals so they come out on the monitor and on the video capture card much better. So the only thing I need to be aware of is I'm doing 25 lines by 80 lines, and I'm switching between the monitor and the VGA capture card. There are slightly different parameters that I need to be aware of, but other than that, the 30 by 80 lines works for both of them, so I'll probably carry on using that. So we have 2 photos of the LCD monitor before and after display enable change, and you can see on the left hand side here that the character kind of goes right up to the edge of the visible area and probably over it a little, and there's a bit of a gap there between the end of the blue and the edge of the monitor. And this is the after one, and you can now see there's clearly a couple of pixels between the character and the end of the blue, and that gap is quite a bit smaller. So that just shows that those adjustments just makes the display fit a little bit better. So originally in this video I was planning to also do the color register, but having looked at the layout, decided that I probably need to do some consolidation and tidying up of the board first before we do anything to do with a colour register, and it really becomes obsolete in the next round of the video. So as we add 2 of these 32K video RAM chips in, we're going to be able to do foreground and background colour anyway, so really the colour register at this point in time isn't really worth doing, and the board is a little bit busy. So if we have a look at the top-down layout, you can see here that if we wanted to add a register and feed the buffer here, we're going to have to move stuff down here and do quite a lot of things around. Now, in fact, what I'm planning to do in the next video is to replace this chip, this chip, this chip, this chip, this chip, and this chip, all with one 24-pin PLD. So programmable logic device. I've worked out that I can probably get virtually all of the functions of these different chips into one PLD. So I'm planning to do that in the next video along with all the video RAM changes. So that's going to clear up quite a lot of space on the board. So for now, that's what I'm planning to do. In the next video, we're going to be doing quite a major rework of the video controller, in that we're going to be swapping out the large video RAM chip here, and we're going to be replacing it with 2 slightly smaller physical chips, but they've actually got about 16 times as much memory, and this is going to allow us to have 16 foreground background colors by character, and will also in the future number 6 and 7 will allow us to do some higher resolution graphics. If you don't want to miss out on future videos, please hit subscribe, and if you enjoy it, please hit like as well. Thanks for watching.